This is SpaceTime, Series 26, Episode 1. Coming up on SpaceTime, how spiral galaxies lose their arms. The asteroid Ryugu sheds new light on the solar system's history. And Solar Orbiter solves one of the sun's great magnetic mysteries. All that and more coming up on SpaceTime.
Welcome to Space Time with Stuart Gary.
A new study suggests that spiral galaxies, like our own Milky Way galaxy for example, tend to lose their spiral arms when they lose the molecular gas needed for star formation. The findings, reported in the monthly notices of the Royal Astronomical Society, are based on new computer simulation tools using artificial intelligence to accelerate their learning. Ever since the Hubble tuning fork, sometimes referred to as the Hubble sequence, which classifies galaxy morphologies, was invented back in 1926, astronomers have been refining their understanding of galaxy evolution and morphology as technology advances. For example, by the 1970s, scientists had confirmed that lone galaxies tend to be spiral-shaped. However, those found in galaxy clusters were more likely to either be spherical and featureless, what we refer to as elliptical galaxies, or flat lens-shaped lenticular galaxies. And the new AI computer simulations may finally have ended the decades-long debate about exactly how spiral galaxies evolve to become either ellipticals or lenticulars. The simulations are showing there's a whole bunch of different things going on when lots of galaxies get packed together. It seems the spiral arms in galaxies are really fragile, and as you get higher densities in galaxy clusters, spiral galaxies start to lose their gas. And this loss of gas causes them to drop their spiral arms, transforming them into lenticular galaxies. On the other hand, when two similar mass galaxies merge, as the Milky Way and M31 Andromeda will do in around 4 billion years' time, they'll coalesce to form a single large elliptical galaxy. To reach these findings, the study utilised the powerful Eagle simulations to analyse a group of galaxies in detail using AI algorithms to classify galaxies by their shape. The neural network-based algorithm can classify about 20,000 galaxies per minute, compressing what typically would have taken weeks into just an hour. And the results of those simulations closely match what's actually been observed in the real universe, giving researchers the confidence to use the simulation results to interpret observations of galaxy clusters. But the studies also identified several lenticular galaxies outside of the high-density regions where they're expected to be found. And here the modelling suggests that they were also created by the merging of two separate galaxies. One of the study's authors, Kenji Becky, from the University of Western Australia node of the International Centre for Radio Astronomy Research, says there's been lots of suggestions over time, but this is the first work to put all the pieces of the puzzle together in a single package.
So in this work, we try to identify galaxies in the supercomputer simulation. So in this simulation, we produce many thousands of galaxies and then try to classify galaxies into elliptical galaxies and spiral galaxies and lenticular galaxies. So lenticular galaxies are very interesting objects because they don't have any spiral arms. And this galaxy can be found in cluster environment or group environment. And on the other hand, spiral galaxy can be found mostly in the field environment where the density of galaxy is very, very low. So the key question of the Hubble sequence is why lenticular galaxy can be found mostly in the group or cluster environment. And this paper discussed this origin.
And what conclusions did the simulation show?
Yeah, so simulations show for the very first time that lenticular galaxy can be formed through gas stripping or galaxy merging in a group and cluster environment.
So you've got these spiral galaxies. The spirals are very delicate, aren't they? And lots of gas there.
Yes.
That's when new stars are being formed. These galaxies, for some reason, are losing their spiral arms and becoming lenticular.
So spiral can keep their spiral arm due to star formation within the gas. So spiral arms are composed mostly of young stars. If the spiral galaxy lose their gas, they can no longer form stars. So spiral arms gradually disappear. So spiral galaxy can be transformed into lenticular galaxy without any spiral arm. So gas is very important for the maintenance of spiral arms in galaxies. So this is a kind of a basic physics. So in a cluster environment, spiral galaxies can lose their gas by stripping, what we call lump pressure stripping. So lump pressure stripping is caused by interaction between cold gas within the disk and hot gas in the clusters. So when the galaxy can lose gas, they can also lose their spiral arm.
So there's got to be a galaxy cluster nearby, and that's drawing the cold gas from within the galaxy itself.
Yes. So the key physical process is a stripping of cold gas. And cold gas can form stars. So if the star formation cannot continue, spiral galaxy can lose their spiral arm.
I guess the other side of the Hubble fork, in this case, would be elliptical galaxies. And I take it that's pretty well understood now. It's merging of spiral galaxies that causes them to convert into elliptical galaxies. What we're going to become in 5 billion years from now?
Yeah. So, galaxy merger can create different type of galaxies. If the mass ratio of two galaxies is larger than 0.3, the two spiral galaxies can be transformed into the elliptical galaxies. But the mass ratio of the two galaxies is very small, like 0.1. These two galaxies can become the S-type galaxies. So the first one is major merger. Second one is minor merger. So major merger can create elliptical galaxies, but minor merger can create S-type galaxies. And this minor merger can happen in the field of a small group of galaxies. So that's the transformation process from spiral into S0 in the small group or field environment. So there are two physical mechanisms of S0 formation. One is gas stripping in the cluster. The other is minor merger in the field of small groups. So there are two ways of losing spiral arm. One is gas stripping, the other is minor merger. And there is a very important distinction between minor and major mergers in galaxy transformation.
So when we see things like the Sagittarius dwarf galaxy being slowly stripped into the Milky Way, is that considered a minor merger?
It's a mini merger. It's not. That's the mass ratio that Sagittarius dwarf to the Milky Way is too small. Less than 0.1. So such merger cannot damage the galactic disk.
Okay.
So it's too small. Yeah. It's like mini merger.
When you put this artificial intelligence program together, were you looking at a particular epoch of the universe? I mean, today or 10 billion years ago? We
can apply this AI to any redshift. So for this paper, we use AI to classify galaxy for the redshift 0, the present universe.
Yep.
This is one of the innovations of this paper because our AI can classify galaxy 1,000 galaxies within 1 second. That's a huge innovation. So far, astronomer has to spend 1 minute or 2 minutes per galaxy to classify a galaxy, but for this AI, it takes only 1 second for 1,000 galaxies. And this is the most innovative part of this paper.
That's astronomer Kenji Becky from the University of Western Australia node of the International Centre for Radio Astronomy Research. And this is SpaceTime. Still to come, the asteroid Ryugu sheds new light on the solar system's history, and Solar Orbiter solves one of the sun's great magnetic mysteries. All that and more still to come on SpaceTime. Scientists studying samples returned to Earth from the asteroid Ryugu have found that it's composed of some of the first solid material in our solar system. The material is known as Ivuna-type carbonaceous chondrites, and it's named after the Ivuna meteorite which landed near Ivuna in Tanzania back on December 16, 1938. Ivuna is one of only 9 known meteorites classified as Ci1 carbonaceous chondrites. And these all have compositions very similar to that of the Sun, meaning they're essentially unaltered since they were formed about the same time as the solar system itself, some 4.6 billion years ago. Put simply, it means they're some of the most chemically primitive meteorites known. The designation CI1 means that Ivuna underwent a high degree of chemical change due to the presence of water. This alteration took place in the parent body of the meteorite at low temperatures, probably around 20 to 50 degrees Celsius, in a water-rich environment. Now, by contrast, chondrites experience thermal metamorphism under dry conditions, usually at temperatures between 600 and 900 degrees Celsius. The findings, reported in the journal Nature Astronomy, show that nearly 2 years after Japan's Hayabusa 2 mission returned samples of the asteroid Ryugu to Earth, scientists are continuing to reveal valuable new information about the early history of the solar system. In this particular study, scientists were looking at the isotopic composition of zinc and copper within Ryugu. It was these isotopic signatures that showed that Ryugu's composition was close to Ivuna-like carbonaceous chondrites. By the way, Ryugu-like material from the outer solar system accounts for about 5 to 6% of the Earth's mass, so we're finding out not just about the solar system itself, but also about our own planet. Meteorites found on Earth give scientists access to samples representing the first moments of the solar system. However, the return to Earth in December 2020 of the Japanese Space Agency's Hayabusa 2 mission provided much more than that. It gave scientists 5 grams of pristine Ryugu fragments, pieces of another world, which had been completely unaltered since their arrival and stay on Earth. The first analysis showed that some isotopic signatures, including titanium and chromium, overlap with other groups of carbonaceous chondrites. So the details of the link between Ryugu and Ivuna-like carbonaceous chondrites wasn't fully understood. Zinc and copper are 2 moderately volatile elements, and they're key to studying the process of accretion of volatiles during the formation of terrestrial planets. The different groups of carbonaceous chondrites show distinct copper and zinc isotopic compositions, with Ivuna-like carbonaceous chondrites being more enriched in volatile elements. So by carrying out the additional analysis of the copper and zinc isotopic compositions of Ryugu, scientists wound up with access to a crucial tool for studying the origin of the asteroid. They found that the isotopic ratios of copper and zinc in the samples of Ryugu were identical to carbonaceous chondrites, but different from all other types of meteorites. By finally confirming the similarity between Ryugu and carbonaceous chondrites, the study establishes that these primitive samples of this asteroid represent the best estimate for the solar composition to date for copper and zinc. The 900-metre-wide asteroid Ryugu is classified both as a NEO or near-Earth object and as a potentially hazardous asteroid of the Apollo group of asteroids whose orbit takes them inside Earth's orbit around the Sun for at least part of their journey. And that makes them pieces of space rock worth studying. This is SpaceTime. Still to come, Solar Orbiter solves one of the Sun's great mysteries, and later in the science report, researchers use artificial human embryos to study how the human spine is created. All that and more still to come on SpaceTime. New data obtained by the European Space Agency's Solar Orbiter spacecraft has found compelling new clues about the origins of one of the Sun's great magnetic mysteries known as magnetic switchbacks, and how their formation accelerates the solar wind, the stream of charged particles flowing out from the Sun which encompass and bathe the Earth. Solar switchbacks are weird. They're a sudden and large deflection of the solar wind's magnetic field. The new observations by Solar Orbiter provide scientists with a first full view of the structure, confirming the hypothesis that it has an S-shaped character. But it doesn't stop there. The findings also showed that these rapidly changing magnetic fields have their origins near the Sun's surface. While a number of spacecraft have flown through these puzzling regions before, in situ data has only previously ever been measured at a single point in time. Consequently, the structure and shape of the switchbacks had to be inferred from plasma and magnetic field measurements taken at just one point. When the German and American Helios 1 and 2 spacecraft flew close to the Sun back in the mid-1970s, both probes recorded sudden reversals of the Sun's magnetic field. These mysterious reversals were always abrupt and always temporary, lasting from just a few seconds to a number of hours before the magnetic field switched back to their original direction. These magnetic structures were also probed at much larger distances from the Sun by NASA's Ulysses spacecraft in the late 1990s. But instead of a third of Earth's orbital radius from the Sun, where the Helios missions made their closest pass, Ulysses operated mostly beyond Earth's orbit. The amount of data available, however, has risen dramatically with the arrival of NASA's Parker Solar Probe in 2018. Parker showed that sudden magnetic field reversals were far more numerous close to the Sun, and that led to suggestions that they were being caused by S-shaped kinks in the magnetic field itself. And it was this puzzling, though still hypothetical behaviour which earned the phenomenon the name switchbacks. A number of ideas were then proposed to try and explain how they formed. Early last year, Solar Orbiter was just a day away from its close pass of the Sun, well within the orbit of the planet Mercury, and it was imaging the Sun's outer atmosphere known as the corona. The particles in the corona are electrically charged, and they follow the Sun's magnetic field lines out into space. As Solar Orbiter was imaging the corona, it recorded a distorted S-shaped link in the coronal plasma, looking suspiciously like a possible solar switchback. Later comparisons of visible light and extreme ultraviolet images of the event confirm this hypothesis. Now, usually active regions are associated with sunspots and magnetic activity, and further analysis showed the speed of the plasma above this region was actually very slow, as would be expected from an active region that's yet to release stored energy. The observations of the plasma resembled a generating mechanism for the switchbacks, an idea first proposed by Gary Zank from the University of Alabama in Huntsville. The hypothesis was looking at the way different magnetic regions near the Sun's surface interact with each other. Close to the Sun, especially above active regions, there are closed and open magnetic field lines. The closed lines are loops of magnetism which arch up into the solar atmosphere before curving around and disappearing back deep into the Sun. Now, very little plasma can escape into space above these field lines, so the speed of the solar wind around this area tends to be really slow. But open field lines are the reverse, emanating from the Sun and ultimately connecting with the interplanetary magnetic field lines of the solar system. Think of them as magnetic highways, along which plasma can flow freely and give rise to very fast solar wind. The switchbacks seem to occur where there's an interaction between the region of open field lines and a region of closed lines. It seems as the field lines crowd together, they tend to reconnect into more stable configurations. Magnetic reconnection is a bit like cracking a whip, as it releases lots of energy, at the same time setting up an S-shaped disturbance travelling off into space. And it's this S-shaped disturbance passing the spacecraft which is then recorded as a switchback. The key observation here was that the switchbacks could be seen emanating from above an active solar region. Late last year, Solar Orbiter made a gravity-assist flyby of Venus in order to adjust its orbit around the Sun, and subsequent Venus flybys will now start raising the inclination of the spacecraft's orbit, allowing it to access higher latitudes of the Sun, heading more towards the Sun's little-understood polar regions, where more mysteries are waiting to be solved. This report from ESA TV.
Solar Orbiter will help answer fundamental questions about the Sun's activity. After some 20 years of development, 6 years of construction and more than a year of testing, engineers have had the challenging task of designing a mission to make detailed observations of the Sun, capture the closest ever pictures of our nearest star, and the first images of the poles.
The spacecraft has a number of key new technologies that have been developed just for the purpose of flying close to the Sun. We have a specific heat shield designed just for Solar Orbiter that will reach temperatures of over 500 degrees centigrade on the front side and will keep things as cool as just about 50 degrees centigrade on the backside to protect the sensitive electronics.
The Sun generates a bubble of plasma enveloping the entire solar system. Known as the heliosphere, anything within it, including Earth, is subject to a stream of charged particles called the solar wind. Violent space weather from flares and coronal mass ejections has the potential to damage satellites, disrupt communications and knock out power grids on the ground.
One of the key questions the scientists have is how the heliosphere is actually generated and how it's accelerated. So what is really driving the solar winds? And the second key question of the mission is understanding what makes the Sun change or vary over this 11-year cycle that we all know. So understanding the magnetic properties of the sun and how these change over this 11-year cycle is one of the key scientific objectives of Solar Orbiter.
To measure the magnetic environment around the Sun, Solar Orbiter is fitted with a suite of 10 extremely sensitive instruments. And so it can take pictures, the heat shield has peepholes through it, covered by protective doors.
We're going to places where no other solar telescopes have been before. We're going to be very close to the Sun to take very high-resolution images of the Sun, unprecedented spatial resolution, and we are also going to fly over the poles of the Sun, regions that are very much unknown because we don't see them very well from Earth, but they are the source of the fast solar wind and therefore are very important.
Solar Orbiter will take several years, using the gravity of Venus and Earth to reach its operational orbit. But once in position, the spacecraft will take measurements that complement NASA's Parker Solar Probe, which launched in 2018.
We will not get as close to the Sun, but we will have a vastly bigger payload complement, so more instruments with more cameras looking at the Sun. So we will do science that is complementary to Solar Probe, and the two will really have a great deal of synergy.
This is Space Time. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.